Hello, welcome back. We have the last section in chapter 4, and we're going to talk today about how to use the equation in model, the logarithm and exponential equation in modeling some applications. So we're going to talk about two different applications today. One of them is about the growth, and the other one about the decay. So let's start with the application, the equation first. So we have to know that the equation is A equals A naught e to kt. So this is my the model. This is the equation that I use to model any application, and I have to define that A is the amount, could be the population, could be money, could be anything. A naught is always the initial value. Initial population, initial number of grams of substance, initial principal, and so on. K. This number is a constant that shows two things, either the growth or the decay. If K is greater than 0, then it shows, we call this growth. And if K is less than 0, we call this model decay. Alright? So based on these two, we're going to learn how to model an application. So let's see. I have a model here. A small city. Had 5,000 people in 2005. And 6,000 people, or 6,200 people in 2010. So now we need A to create the model. Okay, so now I have the 5,000. This is the initial value. So this is A naught. Okay? And I need to find K. So I have this one, E is fine. I need to find K. And this is going to be in a function in terms of T. So I need to find K. My goal is to find K. So how can I do that? Here, there is extra information giving that the number of people in 2010 is 6,200. So that means that A in 2010, when T is something, and we're going to find it right now, okay, is 6,200. So I can use this to compute. Okay, let's see how it goes here. So this is the initial time, so I'm going to call this T 0. Okay, so if 2005 T is 0, what is T here? So the distance between them, or you subtract 2010 minus 2005 to get here T is 5. In other words, okay, after 5 years. Okay? So let's use that model, okay, to get K. So I have A, this is A, 6,200 equals A naught. Where is A naught? Here it is. 5,000 times E. Do I know K? No. Do I know T? Yes, because it's in 2010, so T is 5. So K times 5. That looks like a familiar problem that we worked on it last time. So we need to find K. K use the natural log. And we use natural log because we have E. First of all, we divide by 5,000. both sides to isolate E. And the reason of that is we need to use the natural log. You can't use a natural log with a coefficient of E. Okay? So here this number, I believe that we got 1.25. Okay? Equal E to 5k. Alright, we're going to take the natural log of both sides. So the natural log of 1.25 equal the natural log of E to 5k. But based on the rule, the natural log of E to something is that thing. So natural log of E to 5k is 5k. So natural log of 125 is 5k. Now we can divide by 5 and compute k. You use the calculator. If you use the calculator to compute the natural log of 1.25 by 5, I think you would get 0.0, I computed before, 30. Just to be careful here, if you can store that number in your calculator, that would be better, because else this is not going to be accurate. But if you can store it, that would be better. Okay, now let's write this model. So now I have the model. A equals A naught 5,000. E to k, I got k, 0.0430 t. So now this is my model. The second question is asked about predict the number of people in the city in 2030. So predict the number of people in 2030. So the first thing that you have to do that, so I want to get A and the time 2030. First of all, I need to interpret 2030 to t. So how much is t in the year 2030? The easiest way to do that is to subtract 2030 minus 2005. And now I get t is how much? Is 25. Now, I plug the 25 here and compute A, and this is the answer to the question. So A is 5,000, E to 0.0430 times 25. So we multiply this 2 and raise the E, and then multiply by 5,000, and you got rounded is 14,658. Okay? So again, the model, you have to compute k first. And then, after you compute k, you may be asked about to do something like predict number in the future or in the past, and you're going to find the growth after a certain year. Another kind of question is to ask you about decay, and I ask you about when a substance arrive to a certain amount. So we're going to see that in the next example. So I'm not going to ask you about the amount, but I'm going to ask you about the time. Well, let's see. So the first step is always finding the model. And here's my model. Okay, so a scientist had 30 milligram of a substance. After 4 hours, the substance had decayed to 25 milligram. So it was 30 and went down to milligram. We need to find a model first, and then we're going to find how long does it take the substance to reduce to 4. So let's get the model first. Let's define what I have here. So number one, I have the substance, the scientist had 30 milligrams. So 30 milligrams. How can I call this? This is the initial amount of the substance that I have. So this is A naught of a substance after 4 hours. After 4 hours. So this is T. So here's T. So how much is T here? T is 4. Okay, the substance had decayed to 25. So this is A. So when A is 25 with times 4, okay, and the initial amount is 30, I can get K. So let's write this one. I have all the information, and I'm going to write this one and solve for K. Be careful here. K must be negative because it's decay. I told you here, if it grows, K would be positive. But if it's decay, it must be negative. So when you answer this question, and if you get a positive K, make sure to revise your question because there must be something wrong. Okay, so A, what is A here? A is 25. This is A, 25 equals, please help me, A naught is the 30, and E to K. Do I know K? No. So K, T, I have T. T how much? Where's T? Here it is, 4. Now, first of all, I divide by 30. I have 5, 6 here, equals E to 4K. Okay, again, I'm going to use the natural log. Whenever you see E, use a natural log. So I have the natural log of 5, 6 equals the natural log of E to 4K. Natural log of E to something is this thing. I have here the natural log, let's write it down here. The natural log of 5 over 6 equal 4K. And we divide by 4 and compute K. So I divide by 4, so I have K is the natural log of 5, 6 divided by 4. And how much did I get it here? I got here, that is negative 0.0456. So notice something here. This is a fraction. The natural log of any fraction must be negative. And this is positive, so negative over positive must be negative. If K is positive, I can't consider that decay, but I will consider that growth. But we're talking about decay here, so K must be negative. So now, I got K, and I'm going to write my model. I'm going to write my model here. A is A naught. How much is A naught? 30 times E to K. What is K? Negative 0.0456. So E to negative 0.0456. And T. So this is my model. I think that if you keep practicing that would be easy to find that solution. The next part is asking about how long will it take for the substance to be reduced to 4 milligrams. So how long? So I'm asking about T. T is how much? so that the amount, so A is 4 milligrams. Is that clear? So now, let's think about that. I'm going to write my model down, but I'm going to write A is 4. So I have 4 equals 30 times e to negative 0.0456 t. I don't know t. That means how long? I need t. Alright. First of all, divide by 30, because I need to isolate e and use the natural log. So divide by 30, divide by 30. So I got 1 here, and I got 2 over 15 equals e to negative 0.0456 t. Okay, what's the next step? Take the natural log of both sides. So I have the natural log of 2 over 15 equals the natural log of e to negative 0.0456 t. And here the natural log of 5 over 60. I don't know, I'm writing 5 all the time. The natural log of 2 over 15 equals, the natural log e to something is the same, so equals negative 0.0456 t. And now we solve for t, so I divide by negative 0.0456. So I have t equals the natural log of 2 over 15 divided by negative 0.0456, which is equal, I got here 44.205 milligrams. Okay? So, I'm sorry, that's hours. So it's time, so must be in hours. Okay, so what does it mean? That means that it takes this substance, this 30 milligrams, 44.2 hours to be 4 milligrams. So the decay is really, really fast. Okay, and by the end of this example, I'll be done with this chapter. I hope that you are good with this chapter. If you have any question, please don't hesitate to ask me. Thank you, and see you in chapter 5 and the system of equations.